High-speed systems are recording.
Roger. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
If you didn't know, I used to work as a part of the SLS program, and in that, I became really familiar with the rocket, its systems, and what kind of makes it unique and a real powerhouse for exploration. SLS is a super heavy lift rocket currently in development and intended to supersede the Saturn V as the strongest and most powerful rocket ever built. It uses modular design that assembles from a bunch of core pieces that can be switched out and swapped as upgrades are produced, designed, and implemented. It allows you to kind of have a modular launch system where as the technology develops, you can upgrade pieces of it and increase its capability as you go. And a big part of its capability is the booster. So on SLS, much like the space shuttle, the solid rocket boosters are a very, very important element of the vehicle. They do a majority of the thrust in getting it initially off the ground, and as a result, they provide most of the control during the early ascent section. On the actual SLS and space shuttle, the boosters have an exceptional range of thrust vectoring. They are able to control the vehicle in pitch, roll, and yaw by working in concert together using their rock and tilt actuators. These actuators are actually located at 45 degrees to the principal axes of the vehicle and give it a lot of control authority and torque for being able to actually muscle this huge powerhouse of a rocket around. So why are we talking about boosters in SLS? Well, I, in the past, have done my own booster tests and built a model SLS. It was actually my first TVC rocket, and it performed pretty well. The boosters on it were passive, so they only provided upward thrust, and they allowed it to accelerate. The extra upward thrust on this early version of my rocket was really, really required just to get it off the ground. From that flight, I had a bunch of key things that I needed to improve. First of these issues was the separation. The boosters were built to be able to separate at burnout, but they never did. They actually stayed on all the way back onto the ground. The separation system uses twin M3 screws, and these M3 screws fit into holes on the core stage, and they hold the vehicle together when being accelerated, and once the acceleration of the booster dies down, it's able to fall off completely naturally. This eliminates the need for any pyrotechnic devices or anything really fancy. Gravity and acceleration on its own are just enough to push things apart. The nice part too about being screws is I can use the threads on them to tighten them and adjust them for a nice, easy separation and fit. After things have separated, a small parachute in the nose of the booster opens up and it's able to be recovered safely. This differs a little bit from the real SLS, which, due to cost constraints, it's actually more expensive to try and parachute in and reuse the boosters. But for me, it works just fine. In the first flight, I had really, really bad issues with roll rate increasing. This came from a misalignment of the two boosters and no control on the roll axis. To solve the roll control problem is really, really simple. You just have to basically emulate the real thing and add thrust vectoring on the roll axis. Adding TVC to the boosters allows you to have a lot more control authority, but it also makes things more complicated and heavy. So, as a result, I came up with a happy medium, which is one-axis TVC. By only using one axis of thrust vectoring, I'm able to make a much, much simpler system where everything's run off of one controller versus multiple. Normally, you would need an output for every single servo, and you might even have a controller in each booster. But by making it only one axis, it's a lot simpler, and then I'm only running 4 servos as opposed to 6. This extra simplicity lets me keep the weight down and raise the performance of the whole vehicle. Each booster is essentially dumb, where there are no electronics in it other than servo, and its wiring is run all the way up the side of it back into the main flight computer. A little quick disconnect at the top of each booster falls away when the booster falls away and disconnects the electrical wires. I was really inspired by some work I've seen from a Swedish group who go by the name Gruyere Space Program. They do absolutely amazing stuff in the extra small scale. They're building rockets that basically would fit inside of a lot of my rockets, just based on diameter and size. But they get a lot of efficiency out of their airframe, and they've come up with a really neat gear-driven TVC mechanism. That type of mechanism, I think, is absolutely perfect for this type of setup. It fits in a really small package, and it provides a lot of fine control and torque. It also isolates the servo from the thrust path of the motor, and puts it right into the airframe, which is what you really want. Inside the booster is some thermal protection system in the way of a piece of cork that protects not only the plastic of the gimbal, but the servo that's directly in the ejecta path of the motor. A lot of hot gas is really concentrated right in the middle of the servo, and as a result, it's not a pleasant place to be, and this cork is a really cheap, inexpensive, and easy to replace way to save that servo the trouble of being blasted with a few thousand degrees of heat. I found this design worked really well. It has great fine control, great responsiveness, and it fits really well into this form factor. Next up, all I have to do is print out another one, assemble it, and put it in the other booster that's basically done and ready to accept it. From there, it's just a matter of re-prepping my SLS for flight again and getting it in the air. So yeah, be looking out for more videos on this beast of a rocket. I have a lot going on with it, and I'm really excited to get it back in the air. So thanks for watching, and I'll see you in the next one.
Houston, you are go for TLI, over.